Let's look at another example. Example 3, say we have a slope of angle alpha, and we have a block of mass m sits on it. Assume there is no friction. No friction. And we know that obviously there is a mg and there is a fn, which is perpendicular to contact surface. If there's no friction, this block is going to slide down, that's for sure. But now our problem is that there is a force, horizontal, pushing this block. So look at this. This block obviously is going to move up the slope. So the displacement, let's say start from here, is s. Since the object starts from the initial location and accelerate up the hill, our question is, what's the final v after it moves up the hill by s meters? Well, we can solve this problem by using chapter 5's technique, and we can give a try. Then we can solve this problem by using what we learned about work and kinetic energy theory. We'll get the same result. The chapter 5 technique is we need to split this force parallel to the hill, and this is perpendicular to the hill. So, and also we split the gravity parallel to the hill and perpendicular to the hill. So it kind of is already pretty messy. That's why that sometimes the chapter 5's technique, it's not the most efficient way of solving problem, but still, let's give it a try. So we have, as a matter of fact, up the slope we have this force, and that is the force against. So we say the acceleration up the hill is caused by f, this component, because this is alpha and this will be alpha. It's caused by f cosine alpha, subtract the gravity's component, which is mg of, well, if this angle is alpha, then this angle is alpha. For mg, see, look at this. If this is mg, and this angle is alpha of the slope, so this portion is actually mg of sine alpha. Okay, so mg, the slope has an angle alpha, so mg of sine alpha. Up force subtract down force equals the mass times acceleration. And the final velocity is the acceleration is constant. Final velocity we can solve by, because acceleration is constant, then we say v final square minus v initial square equals to 2a delta x. In this case, our acceleration is up the hill. Our displacement delta x is s, also up the hill. So up the hill is positive, for example. Then we say initial velocity of the block, let's make it equal to 0 starting from rest. So we say v final after it travels a displacement s, that equals to 2a. What's a? We can get a from here. Okay, so it looks like a equals to of f cosine alpha minus mg sine alpha divided by mass m, that gives us acceleration, and delta x is s. That is the final velocity square. Now what if we use the technique we just learned from chapter 7? Then we say, okay, how many forces? We have obviously gravity, okay, and we have obviously have a normal force. See, this is the direction of slope, so normal force is this way, Fn. This actually is the displacement direction, slope direction. And we have, so have second one, and then we have a force which pushes. So let's make that force of right here. That force pushes F. Okay. So work done, obviously displacement is along the slope, so Fn doesn't do work. 90 degrees. For mg, if we split, the mg of cosine alpha portion doesn't do work because 90 degrees. It is the mg of sine alpha portion does work. It does negative work because you see mg sine alpha is down the hill, s is up the hill. So actually work done is from F, the force pushes it, plus the partial gravity, which is mg, the sine alpha portion. Normal force doesn't do work. The mg cosine alpha portion doesn't do work. That equals to 1/2 of mv final square minus initial velocity 0, so it's minus 0. Now how do we get a work done by F? Let me draw the picture. If displacement is this way, F is horizontal. Isn't that true? The angle is actually between, just similar as the ground and slope, because this S is along the slope, so the angle is alpha. So work done by a force is the force magnitude displacement times cosine of the angle between them. That is what we know. And work done by mg sine alpha. Sine alpha is down the hill, displacement is up the hill, so that is a negative because the cosine 180. The magnitude of that force and displacement cosine 180, that's where the negative comes from. So this is the summation of the work done by these two forces and equals to 1/2 mv final square. Now take a look. If we let this 2 go to the other side and divide by m, what we have is that 2 will stay here, and m, as a matter of fact, that this, we have this f s cosine of alpha minus mg of sine alpha. This m will stay here, and the 2 stay outside, and we have this v final square. Look at it. This is exactly same as what we get here. Final square is twice of fs cosine. Oh, wait a minute. That, do we have s? Yeah, this s actually is outside. We can put in. So, and here we also have a s. Right. See this s turn? Actually, we can move outside, and this is S term. So we can solve this problem by 2 different methods. This is called dynamic method by using the force and acceleration and displacement. And the second one is by work done. So probably you'll say, well, if we can solve the problem by using the technique we learned from chapter 5, why we have to learn this work and kinetic energy theorem? Actually, some problem that we cannot use the technique learned from chapter 5. We have to use the work and kinetic energy theory. For example, this is a simple pendulum of length, which is a piece of string of length L, pivot at point O on the wall, on ceiling, of a little point mass at the end of mass M. Assume that there's a force, constant force pushing it. And if a force pushes this way, the ball will start move. However, you know, the ball can only move at the end of the string, so the string is going to change the position. The ball will end up here because it's connected to the string. And let's say this is an angle theta that the string moved. Now from initial position, let's say theta equals 0, to a final position theta, let's ask this question that what will be the speed of this ball? Or you push it, it start to move and start to gain speed. So how do we calculate that final speed? Now in this case, that the force on it, one is gravity. Gravity is a constant. But tension T is not a constant, because we don't know whether it's changing magnitude, but the one thing we're sure, it changes direction. So force T is not a constant. Obviously, a third force, capital F, if we maintain as constant direction and magnitude, we can make it constant. So the trouble is this tension T. So if we use the technique before, sigma F equals to ma, the problem is if one of the force, when we do sigma, which means we add this plus that plus this vector sum, okay, equals to ma. Now, if this tension T changes direction or even magnitude, then the summation of three forces will not be a constant vector, and then your acceleration is not a constant. When acceleration is not constant, we cannot use the equations from chapter 2, which is final velocity, initial velocity, v final square minus v initial square equal to a delta s, that sort of equation. We cannot use it at all. So what do? We have to use chapter 7 technique, which is work done by how many forces? Well, we just add all the work done. That is work done by F plus work done by mg plus work done by that tension T equals to the final kinetic energy minus initial. If this ball starting from initial position v initial equals 0, see, from here, hopefully we can solve work done by this, that, and then we can solve the final velocity after the simple pendulum swing to a new position of angle theta. Now, one thing, work done by tension T is 0. Because, well, even though tension T is maybe, well, first of all, direction changes. Magnitude we don't know, so it's a variable. So we have to follow the definition of variable force dot ds. But if you take a look, for the ball to move, ds has to be tangential. All the ds has to be tangential. Tension T is always around the radius, it's centripetal. So the angle between tension T and ds is always 90 degrees. So we can say tension T, we don't even know the magnitude, but the angle is 90 degrees. That means tension T doesn't do work. That solved our problem, even though it's a variable force, but it doesn't do work, so it vanished from our equation. And all we need to do is to find the work done by gravity and work done by this constant force. That will be relatively easier, okay? Because from initial to final, we can find what is displacement of S, the total displacement, because since both force F and mg are constant, so we just say F dot displacement plus mg dot displacement equals to 1/2 of mv final square, as long as we find the work done by the capital F and by the gravity, and we're set. The last part is about power. Average power defined as work done over time. That, let's look at units. Work done up to now, we haven't mentioned the units yet. Isn't that funny? That is F dot S for constant force. That result a force magnitude displacement cosine of angle. Now whatever happens, that force is Newton and displacement is meter. So Newton times meter. Actually give a new name, that 1 Newton times 1 meter, that equals to 1 joule. So the unit for work is joule. And also I want to mention, since we have the sigma Wi equal to delta Ke, which is the final kinetic energy minus initial kinetic energy. Now, if work is in joule, then the total work done is also in joule. So left side, if the unit is joule, then every single turn on the right side should have same units. So the unit for kinetic energy is joule, is also joule. That is about unit. And then the instantaneous of work done defined as dW over dt.